I'm going to run through an example of how to solve differential equations in MATLAB and Simulink. We'll go ahead and start off with just a simple first order equation. Okay, so here we have a time constant, okay, and that's going to control how fast it gets to the new steady state, and this would be a gain, and this is a differential equation with an input u and an output y. Okay, so this is very common in process control, where you might have a step input on your u of t, and then your output y of t is going to be the response. So this is a common equation. We'll go ahead and simulate this one first. Okay, so to start, what we'll do is, let me go ahead and just move this out of the way here. Okay, keep our equation right here in the upper right. And then, I'm going to go ahead and just start Notepad++, and then we'll run it in MATLAB in just a little bit. Okay, so the first thing that we want to do in solving this is go ahead and create our function. We just need a function that's going to return dy dt, and then we'll call it, let's say, our first order system. Okay, and then we have time and y that are going to be our inputs, and then we maybe have tau, define tau, and we might define k as well, and then we want to calculate dy dt, and so that's going to be equal to negative y plus k times u. Okay, and then I'm going to divide that by tau. You just have to put everything on the right hand side of the equation. Okay, and then you can do and. And then what I'll do is I'll go ahead and just save this. I'll go ahead and just save it to a new folder here, and I'll do this Matlab ODE. Okay. And I'll save this as first order. You want to do it the same name that you did as the function. And let me change that extension to .m. Okay, so to run it as a Matlab script, you just need it as a .m. And you want to change it, you can click yes. If you open it up now, this is going to open up in the MATLAB editor. You can do this in any text editor. Okay, now we need a function that's going to run this. And so I'll go ahead and create a new text document. Now you could do something like simulate.m. Okay, open that up. Okay, and then the first thing that we want to do is maybe just clear the workspace, close any plots that are available, and clear the screen. I always like to do those three things right at the beginning. The next thing we want to do is just go ahead and define our time points where we want to see the solution. This might be something like lin space, a linearly spaced values between 0 and 10. Okay, and there's going to by default have 100 values there between 0 and 10. And then we want to calculate the response y. And we can use something like ODE 23, and let me just put it in first order. Okay, so this is the ODE function. Pops up with a little bit of a help here. I'll put my time span and then my y naught, my initial condition. So I can define that right here if I want to. Let's say that is 0.5. Okay, now it's going to still give us an error here because we don't have the value of u defined anywhere. Okay, but what I want to do now is also just plot t versus y, just to see the response. So if I try to run it, I'll change folder, and it should come up with an error. Let's see if it did. Okay, so it said this u is not defined, undefined function or variable u. So I want to pass that in as an input argument. Okay, so let's say u equals 1. All right. Then I need to just change this a little bit. Just to have an input argument, I need to do the @ sign, and then I'll put my t comma y, and then my first order, get rid of these parentheses, is going to be t comma y comma u. Okay, so here are the 3 arguments that I have, but this ODE function only requires 2, so I have a third one, a third one that's going to be coming in, and so I just need to also augment this first order function to put another input right here. Okay, our u value. Okay, so let's go back and simulate this again. I run it again. There's no solver property on the line class. Okay, so it had a hard time with the plot. T comma y. Oh, you know what? That's because y is going to be a structure. So y dot x is going to be my time values. Y dot y is going to be the simulated values there. So let's go ahead and just I'll call this z then, and my time is going to be z dot x, and then my y is going to be z dot y. Okay, and so let me just go ahead and plot time versus y, and I'll run that again, and then it'll come up with this first order response. Okay, so I just set up, first of all, I set up this function first order.m, where it returns my derivative. I just have to put my derivative value on the left hand side, calculate it, and what's on the right, it'll return it, okay, from this function. And then I want to simulate it here as well. Now this function, just to show you how it works, if I just typed in first order and I had 0.5, well, let's start with 0 time starting at 0.5 and a value of 1, then it's going to return the derivative value. That's dy dt. And the solver is going to do this over and over again. So it might go to 0.1 and say, well, now at 0.6, there's my new derivative value. And as it gets up there, okay, let's say up to 5, and it gets closer and closer to the value of 2, 1.8. Okay, that derivative is going to get smaller and smaller. So you can see that it starts curving off, and that's what this first order function does for this ODE solvers. It provides the derivatives. Okay, and here you have the just a simulate function that'll do that for you. Okay, so let's go ahead and do this same thing in Simulink as well. So I'll go ahead and open up Simulink. Okay, just type Simulink at the command prompt, and then it's going to go through initialization phase. It's going to ask you what kind of model do you want to have. Just go ahead and select the blank model in the upper left, and then we'll just go ahead and start from scratch. Okay, so now we're transitioning from MATLAB to Simulink. Simulink's nice because you can throw a block in there and then be able to simulate it. Now this is a linear model here, so you could do something like a transfer function for. I just want to show you this in the time domain instead. How to add a function, because it's general. You can transfer functions. You can only have linear models in Laplace domain, but with this method, you can have any nonlinear function that you want, any nonlinear differential equation, and it'll calculate it for you. Okay, so we're just going to modify this a little bit. Let's go ahead and create a. I'm just going to go ahead and copy this folder. Okay, I copied it over here, and we'll just call this Simulink ODE. Okay, and so we're going to keep our first order, but we're going to get rid of this simulate. Okay, and this first order is going to be just a little bit different now. we're just going to have input argument x, okay, and then we're going to have maybe u equals x1, okay, and then let's do y equals x2. Okay, and then we'll still return dy dt. So in Simulink, everything's going to come in as a vector, and then we get to split it out into two elements there. We still have our parameters tau and k. So it's just a little bit different than we did it last time. Okay, when you work with ODE integrators, we're just going to do an interpreted MATLAB function here. Okay, so let me go ahead and close out the MATLAB one. And okay, come back to my Simulink model, and first of all, I'll just go ahead and save it. I'm going to save it in the Simulink ODE. Okay, and we'll just call that differential equation example here. Okay, so the first thing I want to do is just open up my library browser, and okay, so it's thinking about it, and then it'll pop up with a list of some choices, and I'll do interpreted. Okay, so just search for interpreted, and then it'll come up with this interpreted MATLAB function that you can add, and it's right here. Go ahead and drag it over, click it, drag it over, and after it gets over there, you can go double click it, and instead of the sine function here as an example, we'll do first order. Now don't put the m there, okay, the dot m, just do first order. Alright, so there you go. Go ahead and click OK, and I'll just rename this as my first order function right there. Okay, now we have two inputs that are coming into this, the u value but also the y value, and one output that comes out, and what we want to do with the output is just use an integrator, okay, to integrate that output and change it from dy dt into y. Okay, so I'm going to use a mouse for this one. Just go and drag it over, connect those. So what's coming out of here is just y, and maybe I want to add a scope. Okay, so this is going to be my y value. I can change the name of this. That'll be y of t. Okay, and then I need to grab a, I'll do a constant. This will be for my u value. Okay, and I'll leave that at 1. Okay, now if I use the mouse wheel, or I can do control, let's see, I think there's a way to do it with the keyboard as well. Mouse works pretty well with that. You can zoom in or zoom out on this. Okay, so now I need a mux function, mux, and that's going to combine two signals together. And I need that because I need to put the u and the return y into this function. Okay, so I'm going to go ahead and just select this one right here. Okay, I've got my u coming in, and now I need to get my, make this just a little bit bigger. Okay, so now I need to get my y in there as well. Just go ahead and right click here. When you come off of this, you just have to do a right click, and then allow you to draw an arrow off. That's one thing that a lot of people miss. And then I'm going to put this in here. Now, in the last example, I had this starting at 0.5. So if you double click this and you just change the initial condition of y to be something, for example, 0.5, okay, and then we're going to simulate it for a period of 10, and that's okay, but you can change it there. Okay, so let's go ahead and run this. Okay, so we had an error, not enough input arguments. Okay, so I had first order. One of the things I forgot to do is change the run directory. And this gets a lot of people when they're working with Simulink. See, I was working still in this MATLAB ODE. I needed to switch over to Simulink ODE to get my new first order .m function. Okay, and then let's go ahead and try it again. Okay, double click this, and it's still thinking about it. Okay, there it is. Oh, I double clicked it one too many times. Okay, so this is the same example that we had before, but now we did it in Simulink instead of, MATLAB alone. Okay, so you could change the initial condition here. The other thing you can do is also add, for example, if you want to add another state to this. Let me just show you how to do that. Let's say I had just one more state. I'll call that z equals x3. Okay, then maybe another. I'll just make this a second order system. And we'll do negative z plus y, and I'll just leave that as a tau there. Okay, so here I have a second order system, still with a gain of 2. And then when I run it, I'm going to get an error. Okay, let's see if I get this error. Go ahead and save it. There's going to be, it's going to complain about the dimensions of stuff. Okay, so what I need to do is in here I can put the output dimensions. Oh, you know what? I forgot one thing. Let me come back in here. Okay, I need to return not just dy dt. I'll do dx dt instead. Okay, I want to get this error because I think it's helpful to see when things are not working. Okay, dy dt and then dx dt2. Okay, so two derivatives are being returned, not just one. And I had to just change what was being returned right up there. I just call that dx dt. Because now I don't just have one, I have two values that are being returned, the dy dt and the dz dt. Okay, so if I come back here, let me just explain that a little bit more. This one is my first equation right here, and then I just added another equation, z dt equals negative z plus y. And essentially what that's doing is it's kind of like you have an input u, and then here's this first equation right here. In Laplace domain, you can always do k over tau s plus 1. Okay, and then I have my y value. Okay, and then this one is going to be a 1 over tau s plus 1, and then that'll produce z. Okay, so this is the first input. This is going to be like an intermediate state, and then this would be like the output. Okay, that would be in Laplace domain, but we're going to do this in time domain instead with this, with this integrator. Okay, so all right, let me move this out of the way. Okay, so back to Simulink now. Let's see if we get this error. Okay, so I'm going to run it, and it didn't like the dimensions. Okay, so what I need to do is sometimes you got to just put in output dimensions. It tries to guess what those are. So I'm going to put 2 here instead of just 1, or negative 1, which tries to guess what it is. Okay, and let me try it again. Okay, that worked that time. Okay, so now I have the 2 states. The yellow one is the y. The blue one is the z value. Okay, so that's a second order system, and if I set this out to maybe 30 and simulate it again, I'd see that they're going to converge to the same 2 value. It's just that the z value is an additional lag of time constant 5 beyond the y value, and you can see that they are kind of tracking together there. Okay, but okay, so that is y and z. So essentially I showed how to solve differential equations. You could just replace these with any other type of differential equation that you'd like to put in there. Nonlinear, linear, just make sure you use this integrator right here, and then loop back those values back in here, because this function that's going to be calculating the derivatives needs the the y and the z values so that it can calculate the next derivatives. Okay, and then it will return these two right here. Okay, so so that's it. This is how you solve differential equations in MATLAB and Simulink.